In this video, we will discuss the last section of Chapter 2 about continuously differentiable functions. Now, as usual, let f be a function from omega to Rm, where omega is a subset of Rn, and f is said to be continuously differentiable on omega, or of class C1 on omega, if all the partial derivatives of each component functions exist at every point in omega and are continuous on omega. And we use this notation to denote the set of all C1 functions on omega. Now, one can also use the term class C0 to denote continuous functions on omega. Now, recall from theorem 2.12 that a necessary condition for f being differentiable is the existence of all partial derivatives of the function. However, we also know that the mere existence of all partial derivatives of the function does not imply that f is differentiable, and we need something more than just the existence. Now, the next result will tell us that f being class C1 would be sufficient for differentiability. Now, here is the proof for theorem 2.18. Now, first of all, due to theorem 2.8, we know that it suffices to prove that each component function fi is differentiable, and therefore we may simply assume that m is equal to 1. Alright? Now, for any a in omega, we first of all look at the difference, fa plus h minus fa. Now, we then expand the difference on the right hand side. And what I'm doing here is that we begin with adding and subtracting a term, with h1 being added to the first coordinate. Okay? And then next we add and subtract another two terms, with h1, h2 being added to the first two coordinates. Now we keep on this procedure until we add and subtract the final two terms with h1, h2 up to hn minus 1 being added to the first n minus 1 coordinates. Now, by doing that, we add and subtract many terms in the middle, and eventually they will be cancelling with each other. And what remains will be these two terms, which is equal to the left hand side. Okay? Then we proceed to the next step. Define a one variable function phi1x to be f of this, with the first coordinate being the variable x, and the remaining coordinates are the coordinates of A. Now note that phi1x is a one variable differentiable function. Now this is because f is of class C1, and by definition, all the partial derivatives of f exist, and in particular, the partial derivative of f with respect to the first variable exists. And this means phi1x is differentiable. Alright? Then we can apply the mean value theorem for one variable functions to get this equation. But phi1 of a1h1 is just this term, and phi1 of a1 is just this term. Moreover, phi1 prime b1 is equal to the partial derivative of f with respect to the first variable evaluated at b1, and hence this term is equal to this term, and therefore we have this equation. But this is exactly the first term on the right hand side from the previous slide. And then we just keep doing similar procedures for the remaining differences. For example, we can define phi2x to be this, and apply the mean value theorem again to express the second difference as the right hand side. And finally, we can use the mean value theorem to express all the differences on the right hand side to get this. And this is equal to the sum of the jth partial derivatives of f evaluated at this point multiplied with hj. Now the final step is to show that there is a linear map L which will make this quotient goes to 0 as h goes to 0. And obviously this is going to be the candidate for the linear map, which is equal to the sum of the jth partial derivative of f times hj. Now then we plug this into the quotient, and then we use the expansion for this term we obtained earlier. We got the right hand side. Then we use the triangle inequality and apply the inequality the absolute value hj over log h less than or equal to 1 to these terms, and we will get this inequality. Now finally, by the assumption that f is of class C1, all the partial derivatives of the function f must be continuous, and hence the difference between these two terms must go to 0 as h go to 0. And the proof is now complete. Okay, now before I proceed, I would like to give a summary on the relationship of several concepts. Now here you can see the logical relationships between several concepts like f is of class C1, f is differentiable, f is continuous, and all partial derivatives exist. Now theorem 2.18, which is the theorem we just proved, tells us that f is of class C1 implies that f is differentiable at A, which in turn implies that f is continuous at A. And moreover, f is differentiable at A implies all the partial derivatives exist at A. This is given by theorem 2.12. Now, however, we also know that this is not sufficient, and we have a counterexample, right? So given by 2.11. And of course, we also know that f is continuous is not sufficient to say that f is differentiable. Now finally, f is differentiable at A is not sufficient to say that f is of class C1. And you will see some counterexamples in the next assignment. Alright? Now I would like to add a further remark here. Now suppose that f is of class C1 on omega. Then for any a in omega, and for any epsilon bigger than 0, there exists a delta bigger than 0, such that for any x in omega with the norm of x minus a less than delta, then the Frobenius norm of f prime x minus f prime a will be less than epsilon. So here these two are two n by n Jacobian matrices. Now I'll leave the proof of this result to you as an exercise. Now the consequence of this result is that if we regard f prime as a map from omega to Rm by n, where this is the space of all the n by n matrices. In other words, f prime will stand upon A in omega to f prime A, which is a Jacobian matrix. Then such a map is continuous on omega if we assume that f is of class C1 on omega. Now this is going to be quite useful, and we will use this result from time to time in future chapters. Okay, I would like to skip the next example 2.19 and leave the details to you. The last part of this section is about higher order partial derivatives, and in general f is said to be of class CR on omega if the partial derivatives of all the component functions fi exist up to order R and are all continuous on omega. In particular, functions of class C2 have a nice property, which is known as the commutative property of partial differentiations, and we will discuss this property in the next theorem 2.20. Okay, so here's the theorem. So as usual, let f be a function from omega to Rm, where omega is a subset of Rn. If f is of class C2 on omega, then all the mixed partial derivatives are equal. And the proof goes as the following. Now first of all, we note that it suffices to consider the case where the function f is a function of two variables. Now the reason is that when we are considering the second order partial derivatives, only two of the variables are involved, and all the other variables are fixed and remain unchanged during the partial differentiation. Now for any a and h in R2, we define a function capital F to be the right hand side. And note that the right hand side is given by the difference of two differences. This is the first difference, and this is the second difference, alright? And there are 4 points being involved in these differences. And here is a diagram showing the position of the 4 points. Now for simplicity, I am drawing this diagram in the case when h1 and h2 are assumed to be positive. Now if you look at the first difference, this is given by f of this point minus f of this point. And if you are considering the second difference, this is given by f of this point minus f of this point. Okay? Now next I define another function phi1x, and this is defined to be the right hand side. And note that the previous function capital F is just the same as phi1 of a1 plus h1 minus phi1 of a1, because phi1 of a1 plus h1 is just the first difference, which is this term, and phi1 of a1 is just the second difference, which is just this term. Now note that phi1x is a one-variable function which is differentiable because f is assumed to be of class C2, and hence D1f exists, and this means the derivative of phi1x exists. Now we can apply the mean value theorem for one-variable functions to phi1x to get this equation. And then by the definition of phi1x, phi1 prime b1 is just equal to this term. And now I can apply again the mean value theorem for one-variable functions to d1f b1y, where y is the variable of this function. And also note that this is a differentiable function because d2 d1f exists. And finally, the function capital F can be expressed as d2 d1f evaluated at the point b1 b2 times h1 h2 for some b1 b2. Now next I would like to go back to the definition of the function capital F and rearrange the terms on the right hand side. Now this time the first difference is given by f of this point minus f of this point, whereas the second difference is given by f of this minus f of this. And then we repeat the previous argument. And here is the detail. So this time we define the function phi2 as the right hand side, and then we apply the mean value theorem to get the difference of the first order partial derivatives. And then we apply again the mean value theorem to get the second order partial derivatives. And finally we arrive at the same function capital F, but the right hand side has been interchanged to d1 d2f at a certain point c1 c2. Now as a result, we have expressed the function capital F in two different ways, and if I divide this by h1 h2, I will get the left hand side equal to the right hand side. And by letting h1 h2 goes to 0 and using the assumption that the second order partial derivatives are continuous, we'll get the result. Alright? Now here is a simple consequence of the above theorem. If we know that f is of class CR, then all the partial derivatives up to order R can be interchanged. Now this simply means the order of the differentiation is not important. Now finally, if we omit the continuity assumption for the second order partial derivatives, then there exists counterexamples to the above theorem. And example 2.22 is such an example. Here you can see that d1 d2f at 0 is not the same as d2 d1f at 0. And of course the problem is the discontinuity of the second order partial derivatives at 0. Okay?